So I've got a couple of questions associated with prime factorisation for you here. What I want you to do is read the questions, pause the video, have a go at them and come back and check your answer with what I'm going to present to you. So here you go. So just 3 questions for you there. I want you to first find the lowest number with 60 factors. Second one is prove that if n is greater than 1, then n squared has an even number of factors in its prime factorisation. And then the third one is use prime factorisation theorem, and the ideas behind it, to prove that the square root of 2 is irrational. So that's going to combine that with the proofs material we talked about before. So pause the video and have a crack at those. So the first one, find the lowest number with 60 factors. Well, the first thing we need to do is do a prime decomposition of this. So how do we break 60 down into prime factors? Well, 60 is actually quite straightforward because 60 is the equivalent of 2 times 2 times 3 times 5. Yeah, we can break it down in terms of our prime numbers to be that. Now we have to ask ourselves is, how do we get a number with that many factors? How do we get a number with 60 factors? Well, one thing that we have to make sure that we understand is that the powers in the prime factorisation can give rise to the number of factors that a number has. So for example, if I was to look at the number 150 and I did the prime decomposition of that, what I'd end up with is that 150 is equal to 2 to the power of 1 times 3 to the power of 1 times 5 squared. So that would be what 150 would be if I broke it down. Now the powers associated with those are 1, 1 and 2. Now 150, if I wanted to, I could go through it and write down how many factors there are for that number. But there's a quick way of doing it. For each of the powers associated with the primes, if I add 1 onto each of them and then calculate the product, that tells me how many factors that number has. So for this one, if I did 1 plus 1 multiplied by 1 plus 1 multiplied by 1 plus 2, so I've added 1 onto each of these, what that would give me is 2 times 2 times 3. What that would then tell me is that I've got 12 factors for that number. And if I was to go through 150 and calculate each of the factors, this is exactly what would come up. I'd get 12 factors. Now I can use that and apply it to this to get the powers that I'm after. So to get the powers of the factorisation, because what I know is that each of these can be reduced by 1. So I'm going to go back the way from what I've got here. So I've got a 2, so that's going to be 1 power. So I've got a 1. 2 is my next power, so again that's a 1. 3 is going to be my next one, so there's a 2. And 5 is going to be the next one, which is 4. Because remember, that tells me how many factors there are. So similar logic to this, that's the powers with 1 added, multiplied together to give me the number of factors. So each of these, if I take 1 off, that tells me the powers associated with the primes of the decomposition that I've got. So in this case, my powers are going to be 1, 1, 2, and 4. So what that means is I can take the first 4 prime numbers, so 2, 5, 7, 2, 3, 5, and 7, and these will be the powers associated with them. And if I then take the product of those numbers, what that will give me is the lowest number with 60 factors. So it's going to be 2 to the power of n times 3 to the power of m times 5 to the power of, let's say, k times 7 to the power of, let's say, a. So if I do that, that will give me the number that I'm after. Now what we're going to do is, in order to keep it as small as possible, we're going to associate the powers going in ascending order, but going back the way in terms of their prime association. Which means that the lowest number for a power is going to be associated with the highest prime number. So if in order to do that, what I'd write it as is 2 to the power of 4 times 3 to the power of 2 times 5 to the 1 times 7 to the 1. If I associate it any other way, so if I was to put 7 to the power of 4, that would make that number much larger than if I associated the biggest power with the smallest prime. So when you're doing it, associate it that way. Put the biggest power with the smallest prime, work your way up, and then if I were to do that, calculate it, and plug it all into a calculator to get my value, I'd get 5,040. So what that means is the number 5,040 is the lowest number that I have that has 60 factors. Now, it could be really nasty here and ask you to list all 60 of them, but I'm not going to. But that would be the lowest number with 60 factors. This idea with the powers associated with the number of factors, that's something that you need to make sure that you remember, because it comes in handy. So we can work forward to find out the number of factors, or we could take the number of factors and work back to get the powers associated with our primes for the decomposition of the number. Second question was that prove if n is greater than 1, then n squared has an even number of factors in its prime factorization. So what we're going to do in order to do this one is first we're going to look at if it's not squared, then we're going to look at if it's squared. So let's imagine I take the number n, and what I'm going to do is I'm going to take it and I'm going to do a prime factorization of it. So it's going to be n1 times n2 times n3. It's going to be all the way up to, let's say, the kth prime times nk. All of those are prime numbers. Now, they may not be distinct, but they're all prime. So this could be, for example, 2 times 2 times 2 times, and then goes on like that. But the bottom line is they each represent a prime number that is a factor of it. If I were to then do n squared, what I'd then have is I'd have n1 squared times n2 squared times n3 squared, all the way up to times nk squared. Now, what that means is that n, this has k factors. So this n has k amounts of factors. Now, this one here is essentially all of this, so the n, multiplied by the n again. So it's twice it. So what that means is that this has 2k factors. 2 times something is always going to be even, so therefore n squared has an even number of factors. In this prime decomposition. Alright, so it's thinking about it along those lines. Fairly straightforward, to be honest with you. The last one, bit more logic required in this one, was to use prime factorization theorem to prove that the square root of 2 is irrational. Now what we're actually going to do is we're going to prove this one using prime factorization, but also using proof by contradiction. Because what I'm going to do is, to start with, I'm going to assume that u root 2 is rational. So because it's rational, I can write it as a fraction. So I know that root 2, let's say it's equal to m over n. Now if I was to square both sides here, what I'd end up with is 2 equals m squared over n squared. So I could then rewrite it as 2 times n squared equals m squared. Now, think about what we talked about previously. If n has k factors, then n squared has 2k factors. So what that means is on this side, I've got 2 times 2k factors in this one. So let's say it's times 2k factors. So what I've got is I've got an even number of factors here, and then I'm multiplying that by yet another factor. I know it seems kind of illogical because I'm multiplying it by another 2 when I say the next bit to you, but that means I've got an odd number of factors, despite it being multiplied by 2. Because I've got an even number of factors here, then another factor I'm adding in. So that means that it's an odd number of factors. If I was to then look back here, m squared, by this logic here, has an even number of factors. Now, what I've done when I've set this bit up here is I've said that both sides are equivalent. However, what I've then done at this point there is I've said to you that one side has odd number of factors and the other side has an even number of factors. So I'm essentially telling you that one side's got an odd number, other side's got an even number. They do not match. So because they do not match, I've contradicted myself. So I've assumed it's rational and that's true. I've then taken and I've contradicted my solution. So I can't get a solution that works for it being rational, which means that that original assumption fails. So because of that, root 2 is irrational. Okay, so it's irrational. And this prime factorization theorem, that comes into play when we're looking at these number of factors here. Alright, prime factorization theorem, we look at prime factorization of both sides, and they have to be equal to each other. Because there's only one way that you can express something in terms of prime factorization. So they have to be the equivalent of one another. But because there's a different number of factors on each side, they can't be. So using these factorization ideas and techniques, we can apply them to different scenarios and bring in other concepts like, as I've just shown here, proofs. These theorems, these ideas, can be applied then to a wider range and a wider variety of mathematical concepts, and they can allow us to really expand our mathematical base and understanding when we're doing work at this level.